We are given a question to explain the definition of continuity and provide an example that is continuous at the point of x equals 2. And we know that for something to be continuous, the limit of it has to exist and the point itself has to exist. We know that for something's limit to exist, it means that the limit from the right-hand side has to equal the limit from the left-hand side. And therefore, we can simply write it out as if we want a continuity at a point of f of x equals 2, then we could just draw a graph like this, where there is a parabola of negative x squared, and at x equals 2, y equals negative 4. And in order to find our continuity, we know that our limit from the left-hand side has to equal the point, has to equal the limit from the right-hand side. And we know that the limit from the left-hand side is equal to negative 4, because if you look at it from here, from the left-hand side, as we are encroaching on the point of x equals 2, our limit is, our y value is going towards negative 4. And we also know that our limit from the right-hand side is also going to go towards negative 4. From here, if we just travel up this line, this graph, and we go all the way up, our y value is just encroaching on negative 4 as our x value goes towards 2 from the right-hand side. So if these two limits are negative 4, that means that the limit does exist at x equals 2, and it's equal to negative 4. And if this graph were to be continuous, then f of 2 would also have to equal negative 4, because there cannot be a hole at a point where it's continuous. And from here, we can also see that f of 2 is negative 4. Therefore, negative 4 is equal to negative 4 is equal to negative 4. This all checks out, and the function would be continuous at x equals 2. Now, for question number 2, we are to find 3 examples that are not continuous at the point of x equals 2. For example number 1, wait, I should probably stop moving this. For example number 1, we see that the limit itself does not exist, because as we are going to 2 from the left-hand side, our limit is encroaching on y equals 1. Because if you follow down this graph from the left-hand side, it's going towards 1. But from this side, right, as you follow down this graph from the right-hand side, it's going to y equals 2, as we're encroaching on x equals 2. That means that the limit itself does not exist. And if the limit itself does not exist, then this function cannot be continuous because the limit does not exist. Over here, we have a graph in which we have a parabola, which is similar to this parabola almost, but it's slightly different. Over here, we have a value of 2, 1, but if you look at it closely, you can see that there's a hole there. That means that f of 2 itself, or t of 2 itself, does not exist. And if there is a hole in that graph, then at that point, that graph is not going to be continuous, because it suddenly stops, it jumps over the hole, and then it starts again. Even though the limit from the left-hand side is going to y equals 1, and the limit from the right-hand side is going to y equals 1. Even though the limit does exist at y equals 1, the function itself is not continuous at the point x equals 2, because the point x equals 2 does not exist. Now, over here, we have a graph that is kind of simpler. The limit as x is approaching 2, right? But over here we see that in the graph, there is no values at all at 2. There is no limit at x equals 2, because there's not even graphs until 0, and it's 0 to the left. And if we see limit as x approaches 2 from the left-hand side, well, there is no point there, so we can't really say it does not exist. And the point itself, well, it does not exist. The limit from the right-hand side also does not exist, because there's no points there. It's just not there. So since the equation doesn't have points or limits at O of 2, then the function is not continuous at O of 2.